I'd like to take a couple minutes just to talk about some basic properties of Laplace transforms. The definition of the Laplace transform involves an improper integral, and in some cases that improper integral won't exist. The value of the integral will diverge, in which case the Laplace transform wouldn't exist at all. There's going to be two conditions that together will guarantee that the Laplace transform exists, which basically are, first, that the f of t doesn't grow too quickly. If it grows too quickly, then even when we multiply it times that e to the minus st goes to 0 pretty quickly. So we can multiply it by functions that grow, but if they grow too fast, if they grow faster than the e to the minus st, then that integral will wind up diverging. And secondly, the function f needs to be at least piecewise continuous on the interval from 0 to infinity. More precisely, the conditions are that the absolute value of ft must be bounded by some positive constant times an e to the alpha t. So it has to be bounded by a constant times an exponential function, at least for all large values of t. It doesn't really matter what happens for t close to 0. A function like that's said to be of exponential order, and that helps that integral in the definition to converge. The other issue is that on any finite subinterval, we have to have a finite number of discontinuities, and at every discontinuity, we need to have both right and left limits of f existing. So in particular, we can't have things like vertical asymptotes, where the function is shooting off to infinity somewhere in this range of values of t. So with those two conditions together, functions are guaranteed to have Laplace transforms. Fortunately, most functions that we're going to deal with in terms of the differential equations are going to satisfy these two conditions. And most functions in application satisfy those conditions. So this isn't a big problem. But it is important to be aware that because of that improper integral, sometimes Laplace transforms won't exist. Next, I want to look at just a couple of key properties of Laplace transforms. One of our goals ultimately is going to be able to find and compute Laplace transforms without having to hammer out those integrals every single time. So we're going to try to find some basic formulas and patterns and then use those to help us to compute other Laplace transforms without having to do the integral every time. The most basic property is the linearity of the Laplace transform. And if we've got a Laplace transform of a sum of two functions, we can simply compute the Laplace transforms of those two functions separately and then add them together. Also, if we have a constant times a function we want its Laplace transform, we can pull that constant out, simply compute the Laplace transform of that function f, and then multiply by the constant. Another property we're going to have is something known as the shift property. If we want to know the Laplace transform of an exponential e to the at times some function, that's going to be the same thing as first find the Laplace transform of just the f. Ignore the e to the at for a second. And then once you found that Laplace transform of f, that thing will be a function of s. Replace the s with s minus a. And replacing s with s minus a simply represents shifting the function by a units, which is why it's called the shift property. We'll see an example of using this in example 7 in a little while. The final item, and this is going to be critical for dealing with differential equations because they involve first and second derivatives of functions, is we can actually rewrite the Laplace transform of a derivative, first or second derivative, in terms of Laplace transforms of the original function. In particular, the Laplace transform of the first derivative is s times Laplace transform of the original function minus f of 0. The Laplace transform of the second derivative will be s squared times Laplace transform of the original function f minus s times f of 0 minus f prime of 0. We'll make use of all three of these properties quite a bit in the days to come. At the bottom of this page, top of the next page, I have proofs of those three properties. I'm not going to go through those in detail right now. The linearity basically follows because of linearity of integrals. Integral of a sum of two functions can be separated into a sum of two separate integrals, which ends up taking the Laplace transform of the sum of the two functions and turning it into the sum of the two separate Laplace transforms. And similarly, constants can be pulled out of integrals, and because of that, they can also be pulled out of Laplace transforms. The proof of property 2 is going to involve working with the integral a little bit and using integration by parts, but I won't talk through all of the details of that. In the next few examples, we'll make some use of these three properties to help us compute Laplace transforms. And again, one of the key goals here is going to be to find ways to compute them without having to do those integrals every single time.